We are pleased to welcome Arvind. Arvind is Easwaran, and he is an associate professor in the School of Computer Science and Engineering at NTU, Singapore. So in the NTU, he has led several projects, including real-time scheduling theory for miscriticality systems. Sorry. And by the way, tomorrow he will take part of the jury of Roberto's Medina's PhD thesis. And this thesis was funded, granted by the chair of complex system. So we are also here for the seminar of the chair of complex system. And also is an advisor of the thesis of Jean Oudot about security and safety concerns in the smart transport systems, and so it's a joint PhD thesis between the IRT, SystemX, NTU, and Telecom Paritech. But today he's going to for a seminar of a joint seminar between the share of the complex systems and the IRT about CyberPhysical systems and AI in CPS. So Arvind, you have the floor.
Yeah, thanks Laurent. So thank you for having me here. So as Laurent mentioned, this is a talk. I had to prepare this talk in a very short amount of time. Initially, I was planning to give a talk on mixed criticality, and Laurent said, no, you should talk about CPS. So I said, okay, let me see what I can do. And then, so this is a very new area in cyber-physical systems. I guess those familiar with CPS are aware that there is a lot more intrusion of, I call it intrusion of machine learning or techniques from the AI community coming into our domain. And as people who've been always concerned about safety and criticality of such systems, I think for me it's a bit of a concern when some new technology starts intruding into the systems. Then we need to worry about assurance and other issues like that. So with that in mind, we kind of started looking at this problem. It's a very popular topic now in the community, in the broader CPS community. I think there are big projects going on, especially in the US. Also in Switzerland, I'm aware of some projects on this topic. So we started looking at this problem about providing high assurance when there is high level of autonomy in cyber-physical systems. So with that in mind, this is a talk essentially centered around this topic. There are two projects I'm going to present. Both are projects which are very early in their stage in terms of results. So if you look at the references I will give you at the end of the talk, they're all papers that are either been just recently published or in the pipeline, accepted to be. In fact, most of my talk is about a paper that will actually be presented in April in CPS week. So it's kind of a precursor to what's going to show up in CPS week. So it's a lot of preliminary results, a lot of interesting questions that I have in my mind. I hope through this talk to kind of stir some discussion in this room and hopefully form some collaborations around the topics that I'm going to talk about. I would of course like to also bring up the point that I have a lot of collaborators. In Singapore, we generally work with a lot of big groups. So some of them are my students. I also work with the industry. So there is a Delta Electronics, which is a Taiwanese PCB manufacturing company. And we have a lot of research projects funded through Delta Electronics. And some of the work here is actually supported by them as well. Okay, so this is the broad outline. A large part of the talk is going to be centered around machine learning and some issues with machine learning and what we are trying to do in that area. The second part of the talk, which is going to be a shorter part of the talk, is about a project on resilience, where we are essentially handling fault tolerance in industrial CPS. It's more of an applied project where we are trying to build architecture for resilience, and I will have some videos for you to see. Hopefully the videos are interesting. Okay, so beginning with the very hot area of machine learning in cyber-physical systems. So what's happening and why is it interesting? I guess we are all familiar now that machine learning techniques are increasingly being applied in decision making and control problems, many of which are safety critical in nature in CPS. Of course, medical decision support systems are very, very, very popular where machine learning has been applied, probably much earlier than, for instance, autonomous driving. But autonomous vehicles are also a very popular thing now. And I guess we are all aware of all the dangers that come with autonomous driving, with the accidents from Tesla and Uber and so on and so forth. So I guess natural questions arise as to how to deal with such systems. So what is the fundamental difference? So what we understand, as we understand, traditionally systems have been designed in a structure which looks like this. You have some data, you have a program which is something that you have written, you have validated, verified, formally ascertained that it is supposed to do what you want it to do, and then you deploy it. And this program essentially takes the data as its input and produces an output, and because you have verified the program, you're kind of confident that the output it produces is what you want in most situations, hopefully. Of course, machine learning is no longer the case. When we bring in components which are learnt, so machine learnt systems, then you have some training information, some training set, training data. There is a computer, there is an algorithm which supposedly learns from this training data. And then if you provide any arbitrary test input, assuming the learning process has been sound, it's supposed to produce an output, a predication, a kind of output which you hopefully trust enough that you can use it in critical systems. So here you see that there is no concept of explicit programming. There is no real explicit design of the system that is going on, right? So the design is autonomous, and that is where the autonomy comes in. And the fundamental property here is that you kind of trust that the data you have provided to this autonomous system is good enough for it to learn what you want it to learn. Okay. So now, given this background on machine learning, so this was like a 2-slide summary of what machine learning is for us. I want to jump into the critical issues that we want to look at. So these are two standard definitions that I picked up from the literature. One is a more general concept of safety, the one on top, and the one at the bottom is a more specific notion of safety as it applies to machine learned systems. So I mean the one on top is a more general concept, and I don't think I want to say much, but I would like to focus on the one at the bottom. So essentially, safety in a machine learned system context refers to techniques or ability of techniques to ensure that these systems behave as intended. So to me, this is the key phrase that we all want to kind of look at in such systems. So what does it mean to behave as intended? So what is the real intention? I guess we need to first ask that question. And then once we are convinced that we are all in agreement on what our intentions are, then we need to ensure that the behavior of the autonomous system is as intended, of course. So there are two components here to safety: what is intended, and how do you then ensure that the behavior is as you intended it to be. Okay. I think they are both key concepts in machine learning safety. So now going back a little bit to ML again. So how does machine learning typically work? How do they try to minimize risks associated with learning? So it's a very empirical approach, risk minimization approach. So you're given a bunch of input variables. Unfortunately, this doesn't show up here, I think. So you're given a bunch of input random variables. You're given some labels associated with these input variables. So this is your training information, right? So this is the training set. Typically in machine learning algorithms, you have something called a loss function. So this is trying to estimate how well your model is performing in terms of the training set or the test input that you provide to this model. And if you look at what this loss function essentially looks like, so the model is that function h that you're trying to learn. It's a mapping from the input variables to a specific output. What you're trying to learn or what does it mean to minimize loss is the equation presented here. It is the expected loss that you want to minimize, and this is what most machine learning algorithms aim to do. And if you look at what is the expected loss, is how much your model deviates from the actual output. Right? So how much the output produced by a model deviates from the actual output. So in expectation, it essentially looks like this. So you look at the loss function of your model versus the actual output, and if you assume you have some probability density function over your input space, then you get this nice equation. Of course, in reality, it's hard to estimate this expectation. One fundamental problem we all have is we don't know this density function. So the probability density function is typically unknown. So what do most systems generally try to do? They minimize this empirical concept of a risk. So you see it's basically a kind of average performance of the model in some sense over the training set or the test set that you provide to it, right? So this is the equation that all machine learned systems try to optimize in terms of minimizing the risk. A fundamental assumption, many times it's hidden, but it's kind of all over the place if you look at machine learning, is that the training samples are assumed to be representative. Representative in many sense, representative in terms of it follows a distribution which is the true underlying distribution of what you're going to encounter on the field. Representative in the sense that it is complete, that the data actually comprises all the parts of the input space that you ever will encounter on the field, and in many other ways. And this is a key issue I'm going to focus on in this talk, because I think this first work of ours essentially tries to address this problem of representativeness of the training set. Because to us, I think, coming from a safety perspective, I don't ever expect the training samples to be representative in the kind of examples that we are going to use these systems in. So that brings us to the challenges to achieving safety in the presence of machine learned systems. So one is this lack of representativeness of the training data. And lack of representativeness comes in two flavors. So one could be that the process in which the training samples are drawn does not really follow the true underlying distribution, even if we don't know what that distribution is, firstly. It may still not follow the true underlying distribution. And second is even if, let's assume, somehow magically the training samples are actually drawn from the true underlying distribution, we still face this very serious issue of incompleteness of data, simply because data that is critical from a safety perspective for us are typically hazard events which are very rare, which means in the true distribution, the probability that this data actually shows up is very low, which means even if you follow this true distribution magically, the likelihood that such a set of data show up in your training sample is very low. So Firstly, it may not be representative in terms of the distribution. Even if you are able to draw samples from the distribution, you may still miss out on some very critical data from a safety perspective. So incompleteness is another issue that we need to handle. And what I would like to argue through this talk is not that I want to solve the problem of representativeness. I cannot make the training sample representative. I don't believe that. But instead, what I want to argue is that given that we are going to deal with this issue, how or when should we trust machine learned systems? So is it possible to say under what conditions can I rely on the output of the machine learned system, and under what conditions can I ignore it? The other issue, which I will not talk much about in this talk, but I think it's also quite fundamental, and probably some of you here are more interested or have some background in this, is the non-transparency of machine learned systems. Unlike traditional systems where you have model-based design, model-based engineering, you know everything about what this program is supposed to do, what this model is supposed to do, we are kind of dealing with pretty much, from a practical perspective, a black box. Right? I mean, if you look at deep neural networks with hundreds of layers, recurrent behavior, we really don't know, and we really don't anticipate to understand what's going on inside that learned system. In fact, I think it's a kind of a paradox. The reason we want machine learning in our applications and why it seems to be so popular or getting so popular is because of this complexity. The fact that we as humans are unable to design sufficiently complex systems which can do these things is primarily the reason why we are now going into these uncharted territory. So if we now anticipate that we will really understand what these systems are doing, then I think we might as well be better off designing them in the first place. So I think this is going to be a key issue. And why is it a key issue? I think I read this somewhere in, so one of the pioneers of deep neural networks, his name is Gary Marcus. I don't know if you know him. So he, in 2018, so last year, he wrote a kind of a paper, kind of a survey. I would say it's kind of a position paper articulating what he considers as the upcoming AI winter. So he anticipates that AI is going to face a huge, long, cold winter in the near future. And one of the reasons he believes that's going to happen is this issue with extrapolation. So machine learned systems tend to be very good with interpolation. So if you give enough data, it can kind of do a good job of connecting the missing points in between those data items. But what it is not generally good at is what we understand as extrapolation. So I give you training samples in some part of the input space, but of course there are going to be parts of the input space that are not covered by the training sample. And how does machine learned system deal with this part of the input space is going to be the challenge that I think AI has not been able to address, including deep neural networks or any of the latest approaches. So extrapolation is going to be a key challenge that AI is going to face beyond CPS. So this has nothing to do with CPS per se, let's say. But of course, it becomes more important in CPS because these are precisely the data points we are very concerned about, because hazardous events are not going to most likely show up in our training samples. So if you're really interested in machine learning and the upcoming AI winter, I encourage you to read up on Gary Marcus and his position on this. It's very exciting. Okay, so given this background, this is what we started looking at. So we are trying to address this problem on the incompleteness of the training samples purely from a statistics perspective right now. Okay, it's still a very heuristic approach. I still don't think we have reached the point where I can consider what we are proposing to be safe enough to be used in safety critical systems, and that's why the title towards assurance. So it's not yet assured. Okay, but it's definitely, I think, the first step, and we hope that this can lead us somewhere in the near future. So what are we looking at? And I think this is the concept at this level is not new. I will also point you to what has been done in the past in this area. So what we want is a very practical technique to avoid unsafe predictions in ML based cyber-physical systems, safety critical CPS. So what does it mean to avoid unsafe predictions? So it's a somewhat related to the idea of fail-safe operation. So if a model is not likely to give a very good prediction in a certain part of the input space or for a particular input sample, then you want to reject maybe what the model is going to say, and you go back to a backup solution, and this backup solution could be a very simple traditional controller for your CPS system. It could even be a human operator. So you just put up your hands and you ask the driver of the car, hey, what do you want to do? I have no idea I don't trust anything here, right? So this, you can view this as a fail-safe operation of the system. In the traditional fault-tolerant community, I think we understand what fail-safe means. So you can think of this as a fail-safe operation, right? At some point, we say machine learned systems, I don't want to trust you. I will go back to my traditional approach. So luckily, this is not a new concept of rejection in machine learning. It's been around. People in the AI community have been looking at this issue of rejection, in particular when to reject or how to reject. And if you look at a rejection model in machine learning, it's a very simple model. So here is an example of a binary classifier. So binary classifier, given some input data, it's trying to predict 0 or 1, let's say, for simplicity purposes, right? So the phi of x here is the output of the model of the classifier, tends to be between -1 and 1. The more negative it is, you are more confident in predicting one end of the classification. The more positive it is, you are more confident in predicting the positive end of the prediction. Somewhere in between, so it's closer to 0. The closer this value it is to 0, you are less confident in your binary classification of, in your prediction, and you want to reject the output of the model in such cases. So typically, a very simple approach to that is to use some threshold. So here T is the threshold that is being used, and you basically say that if the output of the model of the classifier is sufficiently far away from 0 in the absolute sense, then you will use the output of the model to make your prediction. Otherwise, you reject, which means you do something else. Okay? So this is how people have defined the concept of rejection. I'm just presenting a very simple binary classifier, but you can extend this to more complex machine learning based systems. So of course, a natural question here is how to configure the threshold T. That is very domain specific, potentially also application specific, and you need to explore different values of T. But I mean, this is feasible to do. So what is the problem with how rejection is being used as what we have seen, at least in the literature? So if you look at classification algorithms, okay, in machine learning, then the rejection is or the output of the machine learning component, this phi of x, is essentially used as a prediction probability. Yeah. So what it means is that the larger this output in the absolute sense, the more confidence I have in the output of the machine learned system. That's what it is, the way it is used in practice. But in reality, unfortunately, this phi of x is not the prediction probability in any sense of its, in the way we understand probability. Okay? If you look at, I can give you a simple example here. So this figure shows a very simple example. So it's again a binary classifier, right? It's trying to predict blue or red. It's trying to give two colors to the input data. And essentially, you see what the classifier does in this simple case, and it's true as you extrapolate this to more dimensions. So where there is a lot of overlap in the two types of data, it's less uncertain about its output. So these are the boundaries of the classifier. and in the boundary it is less confident, so the output, the phi of x tends to be small. As you move away from the boundary, the output tends to be large. Okay. So essentially all the phi of x is giving me is how far away from the boundary of the classifier I am, which is not necessarily the confidence I have on my prediction. Okay. The probability of the prediction confidence is not related to how far I am or how close I am to the boundary of the classifier. So in particular, to give you an example in this figure, now look at this space here. I mean, there is no training set there. There is no training data there. Why should I have 100% confidence in my prediction in that part of the input space? Seems very strange to me. And from a safety critical perspective, I would definitely not go by this as my prediction probability. So this is the problem. We saw how rejection is being used. So we said, is there a way to come up with a different metric to do the rejection? So we still want to reject in certain spaces, but let's do rejection based on a very simple intuitive approach. So what is the intuitive approach? In a safety critical system, I look at this training set and I say, wherever I have enough training samples, I will trust the model, and wherever I don't, I won't. It's as simple as that. Independent of where the classifier boundary is or other aspects of the system. So independent of the machine learning algorithm, independent of the models being used, of any other things, I want to build a confidence metric which is solely based on training samples, the distribution of training samples in the input space. So this, we started with this. We said, what can we do? Can we come up with a very simple technique to compute this metric? And that's how the idea started. So the key intuition was data density. Can I find dense parts of the input space from a training sample perspective? And I think the motivation again comes from, you can see this is another example. So this is a published paper, and essentially intuitively I think it's very easy to see what is being argued here, which is that if the test samples are very different from the training samples, so what you train on is different from what you test on, then the accuracy takes a big hit even on well-trained systems. So here it's a wall following robot which basically just goes in a clockwise manner in a room. So it's there is a huge amount of training set available on this robot. And if you build a classifier, so the left hand side shows the output of the classifier on the training sample. The right hand side is the test samples, and you see that the tests here, I mean the classifier is completely off. It's completely wrong. So, and you can see the accuracy dropping. So, but this is, I mean, if you look at most machine learning outputs, they will claim accuracy of 99.5, 99.6, and so on and so forth. I mean, that precisely comes from this assumption that training samples are representative. So I always draw my test samples from the training samples in some way. So if you now kind of go away, you get this problem. So, of course, a natural way to look at density to kind of build a confidence metric on the input space to just get training data density is to do some partitioning of the input feature space, right? So you try to split the input space based on density. I mean, intuitively you can do this, right? So you look at the space, you say, okay, there's a lot of data here, I will cut it here. I trust my input, my machine learning output if the test sample falls in this space or this space, but I won't maybe when it falls here. So this is something we can start by thinking about doing this. And then once I am able to do this partition somehow, right, I am able to successfully create such partitions, then I build a score function. So I give some numerical value and I say that this is the score I give to this part of the input space. So if the score is high, I have high confidence on any machine learned model, any machine learning based system, as long as the machine learning process is error free, Okay, I don't have any comment in this talk on the accuracy of the machine learning process itself, assuming it learns well on any given training sample. All I am saying is that if you have learnt well, then these are the regions in the input space where you are likely to make a good prediction, okay, correct, accurate prediction. So this is the basic idea of what we wanted to do. And once we have this score function, okay, somehow we are able to give this quantify this input space, we can then use it in the rejection process, right. So if the score value is very low in a certain part of the input space, you reject. You say, I don't want to trust your machine learning based system anymore. Okay, and then it's very easy to then build rejection models based on this metric. So for regression problems where you're trying to fit some function for a given data, you can basically just use the threshold. So if the score value is high enough, I will use the output. If not, I reject, and you do whatever you want. In the case of classification problems, you can do something more interesting, because you also have this confidence metric coming from the machine learning system itself, which gives this distance to the boundary essentially. You can combine the two. So if the machine learning algorithm is fairly confident about its prediction, and if my score is sufficiently high, I will then probably use your output, otherwise I will reject. Okay, so you can do some things like these. I will show you some results on what happens if you consider both, you only consider one, what are the impact of that, and so on. Okay. So now that we know what we want to achieve as the end goal, the score function, how do we go about doing this? So a very intuitive approach again would be, if the input space is nice and small, you assume, essentially what you are trying to do is that you assume that, okay, there is this training sample which is distributed on the input space. You assume that the empty parts of the input space are also kind of uniformly have some distribution of data, which is the absence of the data essentially, right. So these dots are basically data points which are absent in the input space, and the squares are the data points which are present. And now you take this space and you apply some very classical techniques. So we are actually using machine learning, some very simple machine learning techniques. So these are like decision tree based techniques to do the splitting of the input space. Okay. And it's a simple density partition of the input space. There are some tricks on how to get it working. I will give you some problems that we faced and how we address those. But I want to emphasize that we are using a very standard approach, which exists in the more traditional, maybe 20-year ago AI approach. Okay, so decision trees. So we start with this idea of Gini index, which is what CART kind of gives you. So if you look at this Gini index, it's a very simple statistical measure. So that equation 3 here shows what a Gini index is. So suppose you have a region. So you have partitioned. Suppose you have partitioned the input space sufficiently. So you have a region, okay, a region called R, let's say. Then what this gives you is a measure of how uniform is the input, is the data classification in that region. So if all of the data in that region belongs to one class, okay, then you basically have a very low Gini index there. Okay. But if your data is not all belonging to one class, so if there is some diversity in the data, then you basically have a very high Gini index. Okay. So that's what that equation represents. So once you have this Gini index, then the CART technique essentially does this. Okay. So you try to find the input feature I and a value, split value S along that feature dimension, such that you want to maximize the gain in the Gini index. And the gain in the Gini index is given by the bottom equation there. So what is the current Gini index of a region? If I split this region into two pieces, based on this split, then what is the resulting Gini indices of each of those two partitions. So that's the GR1 and GR2, and also how dense are these partitions. So that's the ratio here. So if you are able to get a low Gini index and a high density partition, then that's a good thing. That's the way to go in terms of partitioning. Okay. So you try to do this. So the larger the gap, the faster you are reducing the Gini index, and it's a heuristic. It's kind of a heuristic approach, as you see. I mean, you're trying to find this space. Okay. So this is CART, which already exists. So we said, okay, can we just apply this? What happens? So we found some interesting challenges. First is when you want to apply something like this on an input space. Now, typically the number of features you have to deal with are quite large. Now, if you look at image, if the input is an image, you have object detection kind of applications, then you are dealing with several input feature spaces. So how do you handle this complexity? Because now your splitting algorithm can take a long time to converge. So one simple technique is to say that not all features are equally important, and this is again that has been well studied typically in interpretable AI or explainable AI. So there is a large community in AI which now has understood that understanding AI is important. So they are now started working on models which are human interpretable or human explainable. So they basically try to identify the whole objective of interpretable AI or explainable AI is to try to identify features that are key in decision making. And once you are able to identify these key features, then you go and ask a human, does this make sense? Are these the right features to be used? And if that makes sense, then you kind of have more trust in the process. So there are several techniques to kind of give importance, to identify feature importance in a given problem. You can do global feature importance. So globally in the input space, maybe a certain set of features are always important. You can also do local feature importance. So you can say that in certain parts of the input space, certain features are important. In certain other parts of the input space, certain other features are important. And there is a whole body of literature which kind of goes in this direction of trying to identify feature importance in different parts of the input space. So given this, we could kind of extend the Gini index, right, with feature importance. So what we can do then is that now we want to do splitting along those features where the importance score on that feature is high. Okay. So you can add the Fi, which is the importance of the feature, into the minimization process, into the maximization process. The other issue that may happen when you go about this process of splitting is you may end up with extremely small hyperrectangles. So these are, you probably split the input space too much to the point that now it's really irrelevant. I mean, you may hardly see any test samples in such a small input space, or it's too complex now to handle. So this is kind of like overfitting, I mean, in the classical machine learning sense, and you want to avoid this kind of problems as well. So again, a very simple technique to avoid this problem would be to use length, so interval lengths when you split, right. So by using this ratio, you can essentially say that larger the interval length of the resulting partition, the more I would trust the Gini index coming out of that partition. And the smaller the interval length, the less I'm going to trust. Okay. So after we do all this, we run the splitting algorithm. It takes some time to converge. It gives the partitions. now we need to define the score function. So once I have a partition, I need to say what value this partition is going to have. So we decided to use a very heuristic and a very, again, intuitively simple score function, and it seems to work well. We will see how long it can be sustained, because we have to try on more complex examples. But the intuition of this score function is rather straightforward. So I want to use feature importance. So now I have a partition. Okay, I am looking at one partition. So that is this R. It has been obtained, and I want to define a quantitative metric to give a score to this partition. So I will use the feature importance. So that gives me the summation over all global features that are important. I will consider them. So the R plus denotes positive samples in that region. So positive samples for me are training samples. So it's essentially a binary classifier, if you see, right? Either there are training samples or there are no training samples. So I just count the number of training samples in that partition. So that's the R plus here and here. And this essentially gives me the length, the interval length along the feature space I am considering. So the larger, so basically the smaller the side length of the feature space, the more important the feature, and the more training samples I have in that space, the higher is the score going to show up as. Okay. The constant here is used just to kind of normalize between the side length and the training sample size, number of training samples. So this is our score function that we want to use. We tried to apply this. So of course the natural question will be, your initial intuition was to start with you wanted to find data density. You wanted a metric to quantify density of input data in a particular space. So why didn't you just use density? So density in this context would look something like this, right? I mean, you just take the number of samples and you take the size of the space and you say that's my density. I think what we realized very quickly is that such a very simple metric may not work well, especially in large dimensional input spaces, because feature importance plays a very key role in the quality of the machine learning output. So features that are important will have a significant impact. And further, what we didn't want is any one feature, any one side length affecting significantly our score, okay? Because this would imply that a small delta IR in one dimension will artificially bloat up the score. So that's the reason we went to this more in kind of nuanced metric. So now let's see how it looks. So of course it's all heuristic, so you can argue, okay, you can do whatever you want. What does it mean in the real sense, right? So we tried to apply it on several examples. I only will present a few in the slides. If you want, I can show you more offline. I have results from others. So we obtained. So we are currently only using global feature importance, but you can as well apply local feature importance. If you have information about local features, then you can apply it here as well. That's not a problem. So we basically use this global feature importance, which is obtained from a random forest approach, and that exists in the literature. And we have tested so far on 3 models. Okay. So neural nets, SVMs, as well as GP, the Gaussian process. So Gaussian process tends to have some better, probabilistically speaking, better ability to have confidence predictions, because it's based on the Bayesian approach. So assuming it has some assumptions about some knowledge, prior knowledge about the weights, distribution of the weights and so on, but at least it tends to be, or believed to be, better than the others. So what I'm showing now to you is the actual results just for the Gaussian process. The rest I can show you offline if you are interested as well. Okay. So in terms of regression, we are going to apply this model for rejection. Okay. So I will show you the results as we change the threshold t, what happens. Okay. So this is the output of the machine learning model. So in our case, the Gaussian process. So the output of the Gaussian process, we use it in our regression. If our score, so phi f of x is our score, the score that I showed you in a couple of slides earlier. If it is sufficiently high, then we apply the output of the GP. Otherwise, we don't. So here are the results. So this is a robot arm, Sarko's robot arm. So I don't know if you're familiar with the data sets in machine learning. But this one is essentially it has 7 degrees of freedom, the arm. And each degree of freedom, so it has 7 joints essentially. And 21 dimensional input space. So the 21 inputs are for each joint. It's about the position, the velocity, and the acceleration. And the output is this torque. So the inverse dynamics of a torque. So basically, what you have is you have a sequence of position, velocity, acceleration for the 7 joints. And what you want to predict is the torque necessary to achieve that trajectory for the robotic arm. So this is the input data set, the training set we took. So we applied this and we basically built this Gaussian process based model. And what you see here is the loss. So loss is that, if you remember, it is the accuracy of the prediction, right? So and what you have on the x-axis is the threshold of our metric. Okay. And essentially what you see here, on top is a box plot without outliers, and at the bottom is a box plot with the outliers. So we also show the outliers. And you can basically see that as the threshold increases, so this is the threshold of the heuristic score that we develop. So as the threshold increases, the loss decreases, and it comes. I mean, in the case of without outliers, you can see the median is it doesn't change much. So the model is already seems to be doing well here, right? And we reduce it to some extent. But if you look at the outliers, you can clearly see that there is a big change in the way the model is behaving. So what it essentially means is that if you are able to pick so here if you, for instance, in this example, you see a threshold of around 0.5 or around that number based on the metric that we have, gives you a very good confidence in the prediction of the machine learned output. The loss reduces significantly in this case. Okay. It goes down from 3.5 all the way to, you can see it's around 0.5, 0.6. So this is one example on a robot arm. There are other examples. We have tried it on some physical processes as well. I think it's an iron ore mining process where they try to predict the amount of silica, and the performance is also very similar in that. You can also see, if you're interested in the standard deviation of the produced output, then you can see that that also goes down significantly. Okay, as the threshold increases. So these are the standard deviation values of the data set, and you can see what happens as we increase the threshold. Okay. Now moving to an example on the classification side. So in the classification experiment, we said as I said, there are 2 kinds of thresholds you can use. So one is this distance to the boundary, which comes naturally from the machine learning side, and one is the score that we designed. And you can ask the question, how can I combine these 2? So we said, okay, let's see, what we wanted to see is whether this makes sense, that you actually trust the model only if the score that we have is high and the output of the machine learning framework is also sufficiently high. So we said, okay, let's see what happens if one or the other is true. Okay, so we consider two kinds of groups of testing samples, right? So one where both are high So I am saying that it is a good place to trust your model, and the model itself is also confident in that space. And the other is where the model seems very confident, but I am not very confident. And we see what happens in these two spaces. So we again looked at a mobile robot. So this is the Cytos G5. So it's a very simple robot. It just follows a wall clockwise. Okay. So it is a 24-dimensional input, and it maps to 4 classes. So 4 classes are the direction the robot has to take. I think it's move forward, turn right, turn left, or sharp right, sharp left, or just a slight right, or something like that. So because it's clockwise. Okay. So, and this is what we see in terms of the output. So the G1 and G2, if you remember, are the 2 classes. So G1 is where both our heuristic and the output of the model seems to be very confident. G2 is where the model is confident, but I am not very confident. Okay. And these are the values for the 2 thresholds, T1 and T2 we are using. And you can see that there are several cases where the accuracy goes up quite high as we start using our threshold. So you see in the case of G1, you can consistently see that the accuracy is higher. Okay. So clearly there seems to be some benefit in using this heuristic score, and in some cases it's quite significant. So here, even in these places, you see where I am only relying on outputs which are very high in confidence from the machine learning system. So 0.95, so which means it's probably far away from the boundary. Okay, that's why the confidence is high. But even there, by using this T2, which is the threshold on the heuristic that we have, the score that we have, you can see that the overall accuracy changes quite a bit. Okay. And I think this is kind of expected, because I think fundamentally just distance from boundary is not a good way to judge the confidence. Okay, so now the natural question will come: what are the limitations of this, and where are we going with this? I mean, okay, this looks like an initial kind of result that we have, and what are the issues that we need to deal with? So there are several. So as I said, in the current experiments, we use global feature importance. I think we need to start moving towards local feature importance. But that is not very hard to do. In the current framework, it's easy to incorporate local feature importance, provided we know what features are locally important in which input spaces. So there are very good techniques available in the machine learning community. For instance, if you come from that community, then LIME is one very popular local feature importance technique. So I think techniques like those could potentially be used in conjunction to use local features in the partitioning as well as in the score function. So note that we use the feature importance in both the partitioning process as well as in our score definition. I know that the score function is heuristic. How to come up with the score function? Is there a better score function? Can I somehow get some assurance that the score function can be trusted? These are some questions that need to be answered. Okay. Can I derive a more accurate score function, and how do I get the confidence that it is accurate? Will it work in all cases? It seems to be general enough. We have tried it on few examples. I have some in the paper as well, and they seem to work, but does not imply that it may always work. Other issue is now when we go to high dimensions. So as you can see in the examples I have shown you so far, I have not yet done object detection, or I have not yet gone into images. Okay. Now when you start going into high dimensions, there are going to be more issues. In general, we may not have enough training data for subspace partitioning. I mean, in general, if I just look at pure raw images, the pixels and the values those pixels can have, and if I start partitioning, most likely I will end up with, if I want a sufficiently low enough Gini index, I will end up with partitions which are too small to be useful. Okay? The hyperrectangles will be extremely small. But luckily, I think from CPS perspective, I really, if I look at an image input for object detection, for instance, I really don't care about the value of a particular pixel. That is not the level, that is not the granularity at which I want to look at inputs. I am interested in much more abstract input space, right? I am interested in contours, I am interested in shapes, I am interested in objects at that level. So, I don't think we should be looking at individual pixels in images when we are trying to do this kind of heuristic measure. What we really need is to abstract the input space into features that are of relevance to us for that particular application that we are looking at the images for. And hopefully then I think taking that approach, we should be able to probably handle the high dimensionality problem that comes with images. So, but images are going to be a challenge, I must admit. I don't have a solution yet, but I hope that by looking at abstractions, we should be able to address that problem when it comes to applying such techniques to images. Okay, I will move on to the second project. This is somewhat light now, it's more like an applied project. So, I will hopefully at the end there is a video as well, so I think it will help things to cool down a bit. So, what is this? So, this is about resilience in industrial cyber-physical systems. So, as I said, I work with Delta Electronics. These are it's a Taiwanese multinational company, and they do PCB manufacturing. So, most likely, if you if you have in the old days, we used to have overhead projectors. We still use them, I guess, in some places. So, the PCBs inside these are typically manufactured by Delta. So, they are a big manufacturing powerhouse. They have huge factories in China, and they are very concerned about Industry 4.0, coming out of Germany. So, they want to adapt to Industry 4.0. So, for them, Industry 4.0 means typically low volume, high mix production. So, in the past, production used to be high volume, low mix. So, you produce millions of one item, and therefore, you have a very structured assembly line, you keep producing millions of the piece that you are interested in. But what they anticipate going forward is that you are going to get requests from customers maybe for 10 pieces of an item, and then you have to reconfigure your assembly line to then make some 10 different other pieces and so on. So, they see a lot of reconfigurability coming into the system, and they anticipate the infrastructure, the cyber infrastructure that currently exists in the industrial processes to change in reaction to this need for reconfigurability. So, traditionally, as they have currently in their factories, they have a very hierarchical structure. So you have the cloud-based processing happening somewhere at the back end. You have the manufacturing, they typically call it MES, manufacturing, I forget now. So, MES is essentially a scheduler, it's kind of a planner for the manufacturing process, right? It schedules the system as a whole. And then you have some controllers, the SCADA and supervisory controllers sitting down there reacting to MES. And then you have the low level devices, the sensors, the actual equipment, the robots and so on. So, what they see Industry 4.0 doing to them is this shift in their architecture. So, now they see the cloud, they see devices, and then they see everything else in between as a mix. So, the hierarchy is, according to them, going away, which means now there is no MES, there is no controller, and there is no distinction between any of these. You are going to have some what they consider edge computing. I mean, if you want the buzzwords, you can throw in all the buzzwords you want, but essentially they see a bunch of smart devices performing some distributed decision making somewhere in the middle here. This gives them flexibility because then it is easy to reconfigure such systems when you want to handle high mix, low volume production. So the reconfigurability is nice, but it leads to some challenges. So one is the complexity increases of the system. The cyber infrastructure now is much more complex. It also increases the potential faults that may show up in these systems. So one of the good examples I can think of is there is a very strong desire to go to wireless communication in such systems now. I don't know, but if you're not familiar, but you may be surprised that even today most manufacturing lines use wired communication because there is too much metal floating around there that they don't trust their wireless communication to actually do the controls. They probably still use wireless to maybe gather some data and do some back-end processing, but there is no control going through wireless. Of course, that makes reconfigurability very challenging if you have wires going around the system. So they want to go to wireless. So if you go to wireless, now you're going to deal with more faults. So they naturally want to provide autonomous fault tolerance, some resilience mechanism, some framework which can monitor the system, look at faults, react to faults, and reconfigure the system in the best possible way when faults actually occur. Okay, so this desire is very strong, and the objective is clear: to reduce downtime. So reconfigurability has to occur. That comes with its price in terms of maybe potentially more complex faults, more distributed mechanisms for handling faults, but they still want things to work well. So we then looked at this problem. We said, okay, what exists and what can we do? So there are a couple of key approaches that we have seen in this area. So we are now looking at decentralized decision making. So we want to handle resilience from a fault tolerance perspective in a decentralized, distributed manner. We don't want to do central decision making here anymore. In terms of decentralized approaches, there are a couple of approaches. They are all middleware or software architecture driven. So they propose certain middleware designs to as a solution to this problem of distributed decision making. So one of them is called ReApps. It's from Vanderbilt in the US, and it's essentially a discovery manager service, a resilient discovery manager service. So discovery manager is very useful in reconfigurability because it gives you plug and play capability. So you can bring in a new device as long as it has the necessary layers to do this device discovery, interact in this device discovery protocol. You just have to bring in the device, connect it to the network, and in a few rounds of communication, the device is ready to do its job. So plug and play capability comes in with device discovery, and what they propose here is an architecture, software platform essentially, to do this discovery in a resilient manner. So when the discovery service itself starts failing, when devices start failing in the system, how does the discovery manager handle these kind of faults? Okay, so it's a kind of architecture, software architecture, a middleware solution to this problem. Another example we have seen closer to where we are now is what is called Island. It's from Spain, and it's again a middleware that supports reconfiguration, timely reconfiguration in a distributed manner in reaction to faults. And it's a very, there are more details. I don't want to go into too much details, but it's kind of a graph-based approach where they maintain a graph of services and how the services, what are the services in the system, and how these services are linked to each other. And whenever a failure occurs in the system, a failure here, for instance, means a service goes down, then they use this graph to react and reconfigure the system based on the available services. Okay? So it's again a middleware solution. So what we wanted to do in this project was something a little bit more formal. We wanted to rely on formal semantics that exist. We didn't want to invent. So we wanted to look at some approach where we can propose a framework, not necessarily a middleware design, which is based on some formal semantics, and then we apply it in this setting of industrial CPS. And what we found is the concept of contracts very useful. So contracts comes from very nearby here. It's from INRIA. I mean, Tom Enzinger and a bunch of people from there have basically worked a lot on assume guarantee contracts. So we try to extract basically the framework from there. So what we use in this work are parametric assume guarantee contracts, hierarchically decomposed and refined as the underlying framework for developing this resilience architecture. Okay. So I will just give you the overview of the architecture and then just show you the video. I don't want to go into details of the framework. So it's a cross-layer architecture. So we want to link all layers of the cyber infrastructure, from the physical devices to the network, to the computation nodes, and all the way eventually to the application layer as well. So application is where our controllers would reside. So this is like the software architecture, and this is our platform. Okay. It's a hierarchical, so modular and composable framework. So we use contracts which are hierarchically decomposed, and then the communication is strictly following the contract hierarchy. So this is not a completely decentralized system, as you can see, it's hierarchical. But there is a specific reason why we didn't want to go to the full decentralized framework, because the hierarchy gives us a very structured way of communicating between components when faults occur. So every component precisely knows whom to report faults to, and every component knows how to react to faults. So whenever a fault needs a reaction, the component knows which other components to inform of such a reaction. In a pure decentralized or distributed approach, this would require some consensus, and that becomes very expensive when you want low downtime. So we wanted to kind of maintain this trade-off between a pure centralized. So pure centralized would be that there is nothing in between, and all the components are reporting information to the root, and all information about contracts and faults, etc., reside on the root. So we kind of decomposed, but we still maintain some structure in the communication. And then the implementation is kind of very standard. We build some observers, very simple observers, okay, which observe contracts at the components. It's as simple as that. So if you ask me what the contracts look like, so these are, as I said, parametric assume guarantee contracts. So assume guarantee contracts means given some assumptions on the inputs to the system, to the component, it provides some guarantees on the outputs as well as inputs of the system. So some relation between input and output. Okay. We are interested in non-functional properties because we look at the cyber infrastructure. So we are not looking at the control algorithm in this project. So we are looking at issues like latency, power consumption, so on and so forth. So non-functional properties is what we model in the contracts. If you look at the logic used in the contracts, then they would fit under, so depending on what property you are interested in, so latency would typically fall under MTL, so metric temporal logic. But if you look at the implementation, it is not complex, so we don't really need to trace back and forth on the events because a true implementation of MTL is not that easy, it's very complex. But it's more or less, in terms of complexity, it's a very simple kind of propositional logic kind of implementation, okay? Because we just need to look for input triggers. If we are interested in latency, we need to look for input triggers until an output is produced. We measure the time taken for these two events. So because it's an industrial project, we have to do prototyping in our lab. So we decided to play with a German toy. So that's Fisher technique. It's a very, we also have industrial modular robots in the lab, and there are some demos on that. But I I mean, that one is more, it's still under development, so I don't have good videos to show there. So this one is a very simple toy. I mean, it doesn't cost much. It's probably 2,000 euros or something like that. And it's a very simple thing. So there are some tokens you see going on the conveyor belt. So there is a color processor. It's a very buggy color processor. It gives you very bad sensing. But its job apparently is to produce an output which tells you the color of the token. So there are 3 types of token, I think, red, blue, and white. Okay, so it's supposed to identify the color of the token. There are light sensors, so you can basically get triggers about when a token shows up. And as the token moves, the objective of this toy is to use these. So there are these ejectors here. You see, they are basically springs. You can activate them. So the objective is there are 3 colored tokens, red, blue, and white, and they all should fall in each one of them respectively based on the color. So this is a nice toy for us because there are some latency constraints. As you see, the conveyor belt is moving at a certain speed. The token shows up. We cannot stop the token. I mean, there is no way to hold the token somewhere. So the processing of the color processor and the ejector being activated should happen in a certain amount of time. So this is the user objective. End-to-end requirement is make sure the white token goes in the right bin, and so on. There are some other aspects here you can control. So we actually we tweaked the device a bit. You can't do it off the shelf. So there is a motor controller here. There is a motor that controls the conveyor belt. So we kind of built some circuit around it to slow down the motor if we want to. So that's a natural way to react to a very complex fault. If your fault handling is not good enough, meaning that you need to degrade performance of this toy, then the natural way to degrade performance is to reduce throughput. Right? So we can slow down the conveyor belt if a fault is sufficiently big enough. So we are able to do that. What else? That's pretty much it. And then there is a pulse counter which is not shown here, but essentially it counts the steps on the conveyor belt. So you see the conveyor belt is made up of steps and it can count. So that's how you know where the token is or when to expect the token at a certain point. Okay. So then we built some control framework around this using some very simple Raspberry Pis, like maybe $10 devices, nothing expensive. And the idea is there is a color processor. I get the color of the token. Based on the color of the token, I decide which bin I should eject this token into, right? Which of the controllers should be activated, and then the final controller, which actually ejects the token into the right bin. There is also a sensor in the bin to tell me whether the token actually showed up or not. Okay, so if I missed, because sometimes there is jitter on the conveyor belt, so the the token may move a bit. So if I don't eject correctly, then it may the sensor can say that. And then we have this motor controller, which is essentially the boss, so which will decide whether to slow down the conveyor belt or not. So that's the overall system. We built this resilience framework around it, so the contract based, just to demo the prototype. And I will just show you the video. I hope, okay, let's see if the internet works for me. Okay, this is too small. I think it should be a link.
We now present the Fischer-Technic testbed that was used in the case study.
Okay, let's see.
There are 2 light sensors, 1 and 2. A color processor, steps on the conveyor belt, ejectors, token bins, and lastly the token. Instead of traditional programmable logic controllers, we introduced 4 Raspberry Pi 3s to hold the control logic of the color processor, bin selector, ejector controller, and motor controller. This diagram shows the flow of operations when a token enters the testbed through light sensor 1. When a token is detected at light sensor 1, this information is passed along to the color processor, which then reads the color value from the color sensor at its expected step. Once a sensor reading is taken, the color information and the step count at which the token arrived is passed to the bin selector. The bin selector determines which bin the token belongs to and calculates its appropriate step for the ejector to actuate. The ejector number and step are then passed to the ejector controller, which controls the ejectors. The motor controller regulates the speed of the conveyor belt, which is determined through the resilience framework. To introduce resilience management and fault injection capability on the testbed, we used Forte, a runtime environment integrated with 4DIAC IDE on the Raspberry Pi.
Just to add, I mean, I don't know if you work with these RKA frameworks, but this one we are using IEC 61499, which is kind of an industry 4.0 compliant standard for programming. So these are, I mean, for us, it's like you can think of it like block-based programming. You create blocks, you connect them. But the tool Forte that we use is very good because you can also specify hardware as blocks. So we have Raspberry Pis defined as blocks in this kind of a setup.
Pi. All the Raspberry Pis are interconnected over Ethernet through a network switch. 4DIAC is based on the IEC 61499 standard, an event-driven function block model for distributed control systems. Our resilience framework, including observers for contracts and resilience managers, is built on top of 4DIAC. Our resilience framework comprises of a 3-level management hierarchy. There are 3 leaf-level resilience managers, 1 level 1 resilience manager and 1 level 2 resilience manager. The first leaf manager uses a parameterized latency-related contract for color processor, and the second one uses a similar contract for bin selector. The third leaf manager on ejector controller uses a contract that deals with the jitter of the token on the conveyor belt. Level 1 manager handles the contract for latency management composed from the contracts of color processor and bin selector. Finally, Level 2 manager uses the root level contract composed of the contracts on the Level 1 manager and on the leaf manager of ejector controller. Leaf managers reside on the Raspberry Pis corresponding to their respective components. The Level 1 manager resides on the Raspberry Pi corresponding to bin selector, and the Level 2 manager resides on the Raspberry Pi corresponding to motor controller, because it controls the speed of the conveyor belt for fault recovery. We introduced the following 6 fault scenarios to compare our framework against 2 other hypothetical designs.
So
we now present the testbed.
Okay,
in its
this is the
operation.
interesting part.
The token enters from the right where light sensor 1 detects it. As the token moves along the conveyor belt,
everything
the
working
color
normally
sensor that follows determines the color of the token. This color information is then passed onto the bin selector, which allocates the bin to the token. In this case, it goes to the first bin as it is white. For fault scenarios 1 to 3, where color processor and/or bin selector report faults, there would be no physical changes made to the system as they have been resolved internally. Fault scenarios 4 to 6 represent more severe faults that could not be handled internally by the Level 1 resilience manager, or that it was
So you can see the motor controller slowing down.
Depending on the severity and combination of the fault information provided by the lower level managers, the system adapts by changing its motor speed to the other 2 slower speeds. A physical fault that occurs on the system, like the token's obstruction on the
kind of
conveyor belt,
stopping
results
it
in a fault
purposely.
detected by light sensor 2. This fault is rectified depending on
So
its
this
detection
one
by light
reacts
sensor 2 and
by
whether the token falls
activating
into
the
correct
second
bin.
ejector.
Thank you for watching. For more details, please read our paper in IEEE Computer.
No, you don't have to read the paper, but yeah. So the general idea is there is this formal framework which is contract based, verifiable. You can use the contract theory to ensure its correctness. And then what we essentially show in the project is how this can then be applied and deployed in an actual system for providing formally verified resilience for fault tolerance. I was talking to Etienne earlier that another natural extension of this work would be to look at security. I mean, attack detection and recovery from attacks. We haven't done it yet, but if you are interested, you want to see how this can be applied, then I'm welcome to talk about that. So I think that concludes the talk. So that was the last slide. Okay.
Thank you.
Yeah.
Are there any questions?
Yeah, maybe on the first part of your talk, you were saying that you're trying to increase the confidence we can have in machine learning techniques, and you're doing that by increasing the requirement we can have on the outputs of these machine learning, in the sense that you're putting more constraints on the acceptance of the outputs.
Mm-hmm.
And by doing this, you might also consider as errors some outputs that are actually normal situations or potentially acceptable situations, which means that somehow you're going to spend some time down in your fail-safe mode than you would have with the regular error estimation technique.
Right.
So would you consider this as a potential extension of your work to try to measure it?
But when you say regular error detection techniques, so what do you imply? Like the ones that are currently employed in
Yes.
machine learning community? But those are, I mean, in the classification example as I showed you, they are not really error detection techniques. They are just some, I don't know, I mean, it's some arbitrary measure of how far away you are from the boundary. I don't even know how that is related to the actual error in the system. Because, I mean, it may just be that the way I gave you the training samples, you had this, these classification algorithms are extremely sensitive to training samples. I can change the training sample a little bit and you get a completely different set of boundaries. Now imagine how much confidence you're going to have on these boundaries. So I personally don't think we can rely on these boundaries enough. So that's why what we want to say is that you want to rely on some other way to judge the quality. And one way to judge is, I believe what I have seen. So if you, assuming the training samples are error free, okay, I've made that assumption. If your training sample has errors, then I cannot do anything there. Assuming your training samples are error free, all I'm saying is that these are the regions where I have some confidence that you would, assuming you have learned properly, you have learned well. That's all. There is nothing more to the approach. So of course, it can, it's a valid point that it may reject the output of the machine learning model in some cases where it is absolutely okay to accept it. So these would be essentially from our perspective considered as the false negatives, right? I mean, yes, there is a risk of that. It's a heuristic, so there is always a risk of that. And what is the cost? The cost is performance probably, because if you're going to do fail-safe, you're going to run some traditional controller, maybe it will ask if it's a car, it's going to ask you to brake, just stop the car because it doesn't know what to do. Yeah, we want to reduce such scenarios. I don't know if it's it's feasible or any easy to get there. So one approach that we have been exploring, so I have some potential collaboration coming up with Continental on this topic. They are very keen, of course, they're worried about they're running out of business because they do hardware, and hardware car, in the future car is not about hardware anymore, right? So they seem keen to do this. So what they believe is that what you could do is, given some training samples, okay, current training samples, of course you can rely on those training samples. So a very simple approach to confidence is to say that I will only trust the output of the machine learning model on the training samples I have seen. So anything beyond training samples I don't trust. So it's basically you have learned nothing. It's like just a data thing, right? You can start from there. But what the Conti believes is that maybe you start from there and you try to perturb the system a little bit slowly, and you start building your confidence around training samples until you build enough confidence, and then you start growing further. So it's kind of starting at a very localized part of the input space where you trust the machine learning model sufficiently, and then you start growing from there. So in such cases, a metric like this could be useful. So what we are essentially saying is, we are essentially identifying that. So given some training samples, we are saying that close to it, around it, I believe you. So it's kind of, I want you to do only interpolation, not extrapolation, right? I want to exclude extrapolation. And then as you do interpolation, as you keep doing interpolation, some of those test samples eventually become your training samples, because you've built enough confidence on those test samples by producing the right output. And then your ability to interpolate increases, because your training size is growing over time, right? And then eventually, hopefully, you cover the entire space and you're able to predict well everywhere. But the idea is that I don't want to extrapolate, I only want to interpolate, because as Gary Marcus says, they cannot extrapolate well.
Other questions? I have a question, well, a bunch of questions. First of all, how do you characterize the importance of the feature in one part of the, because it's non-trivial to me, because if you want to characterize rare events, it may be a combination of sometimes a feature that is not that much important, but is going to be in some situation, in some context, to have a strong impact. So right. How do you determine that?
Right. So if you look at the techniques that exist in the machine learning community on this interpretability, what they essentially do is it's purely sampling driven. So they take a sample, they see what the output looks like, okay. Then they take sufficient samples in a close region around this sample. So it's like the localization of the sampling process, and they, based on the output produced by this black box model, they try to build an interpreter. So which is kind of identifying what features it's kind of using to make its decision. Okay. And then assuming the sampling is sufficiently good, they claim that okay, these are the features that has been used in this part of the input space to make the prediction. Eventually, the idea of interpretability is that you take your what features you have identified as being important, take it to a expert, human expert, and then ask the human expert, does this make sense? Is this the right features to use to make this prediction in this input space? So if the human is confident that that makes sense, then you then rely on those features as being important. In terms of handling rare events, there are also some techniques I have seen in machine learning on handling rare events. So what they try to do is they artificially, so if you don't do anything, then machine learning algorithms tend to ignore rare events even if you provide them, because their probability is so low in the tests, in the training sample, that they tend to kind of ignore the impact they have and they learn nothing from those rare events. So there are some techniques people have tried where they artificially increase the importance of the rare events, for instance by duplicating them in the training samples, by increasing their density in the training samples and so on. So there are some statistical techniques I have seen where they try to do that. But everything is still heuristic, I think, and very sampling and statistics based. So no assurance yet.
Thank you. Questions? Yeah? No. Thank you, Arvind.
Thanks.